Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Muhammad al-Buzjani, a luminary of the Islamic Golden Age, stands as a pivotal figure in the history of mathematics, particularly for his profound contributions to trigonometry and its practical applications. His life, flourishing in Baghdad during the 10th century, coincided with a period of intense intellectual ferment, where the synthesis of Greek, Indian, and indigenous scholarship propelled the advancement of numerous scientific disciplines. Within this vibrant environment, Buzjani distinguished himself through his rigorous geometric proofs, innovative trigonometric techniques, and dedication to solving real-world problems, impacting fields ranging from astronomy to architecture. The intellectual climate of Baghdad during Buzjani's era was one of unparalleled scholarly activity. The city, a major center of learning and commerce, attracted scholars from diverse backgrounds, fostering a rich exchange of ideas. The House of Wisdom, established earlier, served as a hub for translation and original research, preserving classical texts and promoting new discoveries. Mathematical traditions, inherited from the Greeks and enriched by Indian numerals and algebraic concepts, provided a fertile ground for Buzjani's mathematical explorations. He drew inspiration from the works of Euclid, whose geometric rigor influenced his own approach, and Ptolemy, whose astronomical models and trigonometric tables presented both a foundation and a challenge for further refinement. One of the most pressing practical problems of Buzjani's time, and one to which he devoted considerable mathematical ingenuity, was the accurate determination of the Qibla, the direction of Mecca, from any given location, as well as the precise calculation of prayer times, known as salat. These calculations, of paramount importance in Islamic religious practice, required sophisticated understanding of spherical geometry and trigonometry. The challenge lay in accounting for the curvature of the Earth and the relative positions of different locations on its surface. Existing methods often relied on approximations or were limited in their applicability. Buzjani sought to develop more accurate and universally applicable solutions. Buzjani's approach to solving the Qibla problem involved the application of spherical trigonometry, a branch of mathematics dealing with triangles drawn on the surface of a sphere. He developed new trigonometric identities and methods for solving spherical triangles, enabling more precise calculations of angles and distances on the Earth's surface. His geometric solutions involved projecting the locations of Mecca and the observer onto a celestial sphere, and then using trigonometric relationships to determine the angle between them, which represented the direction of the Qibla. Consider, for example, the problem of calculating the Qibla for a city located at a specific latitude and longitude relative to Mecca. Buzjani's methods would involve first determining the spherical coordinates of both locations, then, using spherical trigonometric formulas, such as the law of cosines for spherical triangles, he could calculate the angle at the observer's location formed by the meridian in the great circle connecting the observer to Mecca. This angle provided the precise direction of the Qibla. The accuracy of his methods represented a significant improvement over earlier techniques, allowing for more reliable determination of prayer directions. Beyond his work on the Qibla problem, Buzjani also made significant contributions to practical geometry, as evidenced by his treatise, book on geometric constructions needed by craftsmen. This work, aimed at artisans and builders, provided a comprehensive guide to geometric constructions using only a compass and straightedge. It addressed a wide range of practical problems, from dividing circles into equal parts to constructing various geometric shapes. The book served as a valuable resource for craftsmen, enabling them to apply geometric principles to their work with greater precision and efficiency. A specific example from Buzjani's book on geometric constructions needed by craftsmen is his method for dividing a circle into equal parts using only a compass and straightedge. This construction, essential for creating decorative patterns and architectural designs, involved a series of precise compass arcs and straight lines. Buzjani provided detailed instructions and proofs for each step, ensuring that craftsmen could accurately replicate the construction. The significance of this book lies in its accessibility and practicality, making geometric knowledge available to a wider audience and promoting the application of mathematics in everyday life. Buzjani's work was influenced by earlier Greek mathematicians, particularly Euclid and Ptolemy. Euclid's elements provided a foundation for his geometric reasoning, while Ptolemy's Almagest served as a starting point for his trigonometric investigations. He also drew inspiration from contemporary scholars in Baghdad, engaging in intellectual discussions and collaborating on research projects. This collaborative environment fostered the exchange of ideas and contributed to the advancement of mathematical knowledge. The impact of Buzjani's work extended beyond his immediate circle of colleagues and students. His writings were translated into Latin and disseminated throughout Europe, influencing the development of mathematics and astronomy in the West. Geber of Aurillac, Later Pope Sylvester II is known to have studied Islamic sources, including possible exposure to the works of Buzjani, and to have promoted the use of the abacus and the Hindu-Arabic numeral system in Europe. While direct attribution is difficult to definitively prove, the transmission of geometric and trigonometric knowledge from the Islamic world to Europe during this period is well documented, and Buzjani's work undoubtedly contributed to this intellectual exchange. Buzjani's early contributions to geometry, trigonometry, and practical applications laid a strong foundation for his later work. His innovative methods for solving geometric problems, his refinement of trigonometric techniques, and his dedication to practical applications established him as a leading mathematician of his time. His influence extended beyond the Islamic world, contributing to the advancement of mathematical knowledge in Europe. Buzjani's early contributions to geometry, trigonometry, and practical applications established a strong foundation for his later work. His innovative methods for solving geometric problems, his refinement of trigonometric techniques, and his dedication to practical applications cemented his position as a leading mathematician of his time. His influence extended beyond the Islamic world, contributing to the advancement of mathematical knowledge in Europe. His rigorous approach to mathematics and commitment to accuracy enabled him to tackle complex problems in astronomy, particularly in the realm of interpolation. Accurate astronomical tables, known as Zijs, were essential tools for astronomers and astrologers in the medieval Islamic world. These tables provided predicted positions of celestial bodies at specific times, aiding in tasks such as determining prayer times, testing horoscopes, and understanding the movements of planets. The creation of these tables, however, presented a significant challenge. Astronomical observations were made at discrete intervals, while the positions of celestial bodies changed continuously. Therefore, astronomers needed methods to estimate values between known data points, a process known as interpolation. The problem of interpolation was particularly acute during Buzjani's time. Existing methods often relied on linear interpolation, which assumed a constant rate of change between data points. While simple to implement, linear interpolation could introduce significant errors, especially when dealing with rapidly changing astronomical phenomena. Buzjani recognized the limitations of these existing techniques and sought to develop more accurate interpolation methods to improve the reliability of astronomical tables. Al-Buzjani's extensive astronomical observations and meticulously compiled tables likely served as a crucial foundation for Buzjani's own work, providing a rich dataset to refine and extend. Buzjani made significant advancements in interpolation techniques, notably through his use of quadratic interpolation. Quadratic interpolation employs a second-degree polynomial to approximate the function between data points, accounting for the curvature of the function and providing a more accurate estimate than linear interpolation. While the concept of quadratic interpolation existed before Buzjani, he refined and systematized its application to astronomical calculations. Specifically, Buzjani devised methods for determining the coefficients of the quadratic polynomial based on known data points. He developed practical algorithms that allowed astronomers to efficiently compute interpolated values for planetary positions and other astronomical quantities. These algorithms were designed to minimize computational errors and ensure the accuracy of the resulting values. One specific technique Buzjani employed involved approximating trigonometric functions using power series expansions. By representing sine and cosine functions as infinite sums of terms, he could accurately compute their values for any given angle. These approximations were particularly useful in interpolation, as they allowed him to estimate trigonometric values between known data points with high precision. Although power series were formalized later, his work foreshadowed these developments. For example, consider the problem of determining the position of Mars at a specific time between two known observations. Using linear interpolation, an astronomer might simply assume that Mars moves at a constant rate between the two observations, leading to a potentially inaccurate estimate. Buzjani's quadratic interpolation method, however, would take into account the changing speed of Mars, providing a more accurate prediction of its position. He might use the known positions of Mars at 3 different times to construct a quadratic polynomial that approximates the planet's trajectory. By evaluating this polynomial at the desired time, he could obtain a refined estimate of Mars's position. Buzjani's improved interpolation methods had a direct and demonstrable impact on the accuracy of astronomical tables. By reducing the errors associated with interpolation, he enabled astronomers to make more reliable predictions of celestial events. This, in turn, improved the precision of astrological forecasts, the determination of prayer times, and other practical applications of astronomy. His work influenced later astronomers and mathematicians in the Islamic world who were involved in compiling and using astronomical tables. His techniques for quadratic interpolation and trigonometric approximation were adopted and further refined by subsequent generations of scholars. These methods became standard tools for astronomers seeking to improve the accuracy of their calculations. In addition to his theoretical work on interpolation, Buzjani also made significant contributions to the design and construction of astronomical instruments. He recognized that the accuracy of astronomical observations depended not only on the precision of the calculations, but also on the quality of the instruments used to make the measurements. Therefore, he sought to improve the design of existing instruments and develop new instruments that could provide more accurate and reliable data. One of Buzjani's notable contributions in this area was his refinement of the sine quadrant. The sine quadrant was an instrument used to measure the angles of elevation of celestial objects. It typically consisted of a quarter circle marked with angular graduations and a movable sighting device. Buzjani improved the design of the sine quadrant by incorporating more precise scales and sighting mechanisms. These refinements allowed astronomers to measure angles with greater accuracy, leading to more reliable astronomical observations. He also made improvements to the sextant, another important astronomical instrument used for measuring angles. The sextant typically consisted of a frame with a fixed mirror and a movable mirror. By adjusting the movable mirror, an astronomer could bring the image of a celestial object into coincidence with the horizon, allowing them to measure the angle between the object and the horizon. Buzjani's improvements to the sextant included refinements to the mirror alignment and the sighting mechanisms, which enhanced the accuracy of angle measurements. The impact of Buzjani's improvements to sine quadrants and sextants was significant. By providing astronomers with more accurate instruments, he enabled them to collect more reliable astronomical data. This, in turn, led to more accurate astronomical tables and a better understanding of the movements of celestial bodies. The enhanced precision of these instruments facilitated more accurate measurements of stellar positions, planetary movements, and solar and lunar eclipses. This increased accuracy had practical implications for navigation, timekeeping, and calendar construction, benefiting various aspects of daily life and scientific inquiry. Buzjani's dedication to both theoretical and practical aspects of astronomy highlights his commitment to advancing scientific knowledge. He understood that progress in astronomy depended on both accurate calculations and precise observations. By improving interpolation techniques and refining astronomical instruments, he made significant contributions to both of these areas, solidifying his place as a prominent figure in the history of mathematics and astronomy. His meticulous work on interpolation methods and instrument design directly addressed the limitations of existing techniques, paving the way for more accurate astronomical predictions and observations. The precision he brought to these endeavors underscored the importance of both theoretical rigor and practical application in scientific advancement. Following his significant contributions to trigonometry and interpolation, Muhammad al-Buzjani's intellectual curiosity extended into the realm of number theory, specifically its intricate relationship with geometric problems. He explored the properties of numbers and their applications in solving geometric puzzles, revealing a deep understanding of the interconnectedness between these mathematical disciplines. Buzjani's investigations included the examination of number-theoretic concepts crucial for geometric constructions and measurements. He ventured into the study of Diophantine equations, seeking integer solutions within the context of geometric challenges. These equations, named after the ancient Greek mathematician Diophantus of Alexandria, involve finding integer solutions to polynomial equations, often with multiple variables. Buzjani applied these techniques to problems concerning the sides of right triangles and the areas of polygons, demonstrating a practical application of abstract number theory. For example, consider the problem of finding right triangles with integer sides, a classic Diophantine problem. These triangles, known as Pythagorean triples, satisfy the equation a squared plus b squared equals c squared, where a, b, and c are integers representing the lengths of the two legs and the hypotenuse, respectively. While the concept of Pythagorean triples was known long before Buzjani, his approach to finding and analyzing these triples within a broader geometric framework showcases his unique perspective. He likely explored methods for generating Pythagorean triples and investigated their properties in relation to geometric constructions. Another geometric problem that Buzjani may have tackled using number theory involves determining the conditions under which a polygon can be divided into smaller polygons with integer sides and areas. This type of problem requires a deep understanding of both geometric principles and the properties of integers. By combining these two areas of mathematics, Buzjani could have developed innovative techniques for solving complex geometric puzzles. Although specific details of Buzjani's original methods for solving these number-theoretic problems are scarce, his commentary on Diophantus's asterisk arithmetic or asterisk is a testament to his engagement with the field. Diophantus's asterisk arithmetic or asterisk is a collection of problems dealing with indeterminate equations, which are equations with multiple possible solutions. Buzjani's commentary suggests that he studied and understood Diophantus's methods and sought to expand upon them. This commentary likely included his own insights and solutions to similar problems, further contributing to the development of number theory in the Islamic world. Diophannus's work on indeterminate equations and number theory served as a major influence on Buzjani's work. Diophannus's arithmetic provided a foundation for Buzjani's investigations, inspiring him to explore new techniques and applications of number theory in geometry. Buzjani's engagement with Diophannus's ideas demonstrates the transmission of mathematical knowledge across cultures and the ongoing development of mathematical concepts. The significance of Buzjani's commentary on Diophannus's arithmetic lies in its role in preserving and transmitting mathematical knowledge. By studying and commenting on Diophannus's work, Buzjani ensured that these ideas were available to future generations of mathematicians. His commentary also provided a platform for him to share his own insights and contribute to the ongoing development of number theory. While Buzjani's direct influence on later number theorists might appear less pronounced than his influence on trigonometry, there are possible connections and cross-pollination of ideas between his work and later developments in number theory within the Islamic world. For instance, mathematicians such as Ibn al-Haytham, also known as Al-Hazan, continued to explore Diophantine equations and their applications in geometry. It is plausible that Ibn al-Haytham and other mathematicians were familiar with Buzjani's commentary on Diophannus, which could have influenced their own work. Furthermore, the broader intellectual climate of the Islamic Golden Age fostered the exchange of ideas between different fields of mathematics. Buzjani's work in trigonometry and geometry likely influenced his approach to number theory, and vice versa. This interconnectedness of mathematical disciplines allowed for the development of new techniques and insights that would not have been possible in isolation. Consider the example of constructing regular polygons using only a compass and straight edge. This classic geometric problem has deep connections to number theory. The ability to construct a regular polygon with n sides depends on the properties of the number n. Specifically, a regular n-gon can be constructed if and only if n is the product of a power of 2 and distinct Fermat primes. Fermat primes are prime numbers of the form 2 to the power of 2 to the power of k plus 1, where k is a non-negative integer. Buzjani had explored the relationship between the constructibility of regular polygons and the properties of Fermat primes. While a complete theory of constructible polygons was developed later in the 19th century, Buzjani's work could have laid the groundwork for these later developments. By investigating the number of theoretic aspects of geometric constructions, he contributed to a deeper understanding of the relationship between these two areas of mathematics. In summary, Muhammad al-Buzjani's investigations into number theory and its connection to geometric problems demonstrate his broad mathematical expertise and his commitment to exploring the interconnectedness of mathematical disciplines. His commentary on Diophannus's arithmetic and his work on geometric constructions using number-theoretic principles contributed to the development of mathematics in the Islamic world and beyond. By combining his knowledge of geometry, trigonometry, and number theory, Buzjani developed a unique perspective that allowed him to solve complex mathematical problems and advance scientific knowledge. His contributions underscore the importance of interdisciplinary approaches to mathematical research and the enduring legacy of the Islamic Golden Age. Buzjani's mathematical prowess found tangible expression in his refinement of astronomical instruments, a field where theoretical knowledge and practical application converged. His contributions to the design and construction of these instruments, particularly the astrolabe, quadrant, and sundial, showcased his ingenuity and his dedication to improving the accuracy of astronomical observations. The astrolabe, an ancient astronomical instrument used for determining the positions of celestial bodies, measuring time, and performing other astronomical calculations, had a long history of development before Buzjani's time. However, Buzjani's enhancements significantly improved its functionality and precision. He introduced new geometrical techniques for constructing astrolabes, allowing for more accurate projections of the celestial sphere onto the instrument's surface. These techniques involved intricate calculations and a deep understanding of stereographic projection, a method of mapping points on a sphere to a plane. Buzjani's innovations enabled the creation of astrolabes that were smaller, more portable, and easier to use, while still maintaining a high level of accuracy. Specifically, Buzjani addressed the challenge of accurately representing the altitude and azimuth of celestial objects on the astrolabe space. He developed novel methods for dividing the circular scales of the instrument, ensuring that the graduations were evenly spaced and precisely aligned. This involved applying his knowledge of trigonometry and geometry to solve complex problems related to angle measurement and arc division. His refined astrolabes allow astronomers to make more accurate measurements of the positions of stars and planets, facilitating more reliable astronomical predictions and calculations. The quadrant, another essential astronomical instrument, also benefited from Buzjani's expertise. Quadrants were used to measure the altitude of celestial objects, providing crucial data for determining their positions and tracking their movements. Buzjani designed and constructed quadrants with improved sighting mechanisms and more precise scales, enhancing their accuracy and ease of use. He also developed new methods for calibrating quadrants, ensuring that they provided consistent and reliable measurements. One particular innovation attributed to Buzjani is the introduction of a universal quadrant, which could be used at any latitude. Traditional quadrants were designed for specific latitudes, limiting their usefulness for astronomers who traveled to different locations. Buzjani's universal quadrant incorporated adjustable features that allowed it to be adapted to different latitudes, making it a more versatile and practical instrument. This innovation greatly facilitated astronomical observations and calculations across a wider geographical area. Sundials, instruments used to measure time based on the position of the sun, were also subject to Buzjani's attention. He designed and constructed sundials with intricate designs and precise markings, allowing for accurate timekeeping throughout the day. Buzjani's sundials incorporated his knowledge of spherical trigonometry and solar geometry, ensuring that they accurately reflected the sun's position at different times of the year. He also developed methods for adjusting sundials to account for variations in the sun's path due to the Earth's elliptical orbit and axial tilt. The mathematical principles underlying these instruments were central to their accurate functioning. Buzjani's profound understanding of geometry, trigonometry, and spherical geometry enabled him to design and construct instruments that could accurately represent the positions and movements of celestial objects. His mathematical insights allowed him to solve complex problems related to angle measurement, arc division, projection, leading to instruments with greater accuracy and precision. Buzjani's work on astronomical instruments had a lasting impact on the development of astronomy in the Islamic world and beyond. His improved astrolabes, quadrants, and sundials were widely adopted by astronomers and scholars, facilitating more accurate observations and calculations. His innovations helped to advance astronomical knowledge and contributed to the development of more sophisticated astronomical models. The direct influence of Buzjani's work can be seen in the writings and instruments of later astronomers. For example, the renowned astronomer Ibn al-Haytham, also known as al-Hazan, drew upon Buzjani's geometrical techniques for constructing astrolabes in his own work on optics and astronomy. Similarly, the Persian astronomer al-Biruni incorporated Buzjani's methods for calibrating quadrants in his extensive astronomical observations and calculations. These examples demonstrate the enduring legacy of Buzjani's work and its impact on the development of astronomical instrumentation. The culmination of Buzjani's mathematical work is evident in the interconnectedness of his contributions to geometry, trigonometry, interpolation, and instrumentation. His geometrical insights provided the foundation for his trigonometric investigations, which in turn enabled him to develop more accurate interpolation techniques. These techniques were then applied to the design and construction of astronomical instruments, resulting in improved accuracy and precision. Buzjani's role in advancing mathematical knowledge and its practical applications during the Islamic Golden Age is undeniable. His work exemplifies the spirit of intellectual inquiry and the pursuit of scientific knowledge that characterized this period. By combining his theoretical understanding of mathematics with his practical skills in instrument design and construction, Buzjani made significant contributions to both pure and applied mathematics. His legacy extends beyond the specific instruments he designed and constructed. Buzjani's work inspired later generations of mathematicians and scientists to explore the connections between mathematics and the physical world. His emphasis on accuracy, precision, and practical application set a high standard for scientific research and helped to advance the development of mathematics and science in the Islamic world and beyond. In reflecting on the enduring legacy of Buzjani's work, one recognizes its significance for understanding the history of mathematics and science. His contributions demonstrate the importance of interdisciplinary approaches to scientific research and the value of combining theoretical knowledge with practical skills. His work also highlights the rich intellectual heritage of the Islamic Golden Age and its lasting impact on the development of mathematics and science worldwide. He was a master of his craft, and his influence extended far beyond his immediate circle, shaping the course of scientific inquiry for centuries to come. His dedication to precision and his innovative approach to problem-solving serve as an inspiration to mathematicians and scientists even today.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.